Welcome students. In today's lecture we will be looking at some of the governing equations of fluid flow in order to understand how we can use the computational methods to solve complex engineering problems. So I'll just list down the topics for today and then we'll move forward with our discussion. So in today's lecture we will be covering the concepts of mass conservation, momentum conservation, as well as energy conservation equations, so that we will be able to model the behavior of a fluid in case of any engineering problem. Because when you speak about modeling of fluids, it is pretty much important that you are able to mathematically model the fluid so that you can apply it to the you can make use of the computer science in order to solve the fluid flow problem. So we need to mathematize the models for starting our problem. So for example, let us have a curious case where I am going to have a duct which is shaped like this, and I am going to have water that is flowing through the duct like this. So obviously the pressure at this side will be P1 and this is going to be P2, and P1 will be greater than P2 for the flow to happen in a direction as I have indicated. And let me say that the density of the fluid is rho and the velocity of the fluid at section 1 is C1. Let me say that the area of the cross section is A1. And if you are going to visualize what will happen at section 2, we must have the similar set of parameters to compare both the mass flow inlets and the outlets. So we will have rho 2, A2 and C2. So according to mass conservation, the mass cannot accumulate inside the system. So obviously if you are going to have the mass that is going to get accumulated in the system, then it will start to saturate and the fluid flow cannot happen. But in a steady state we know that fluid will transfer through this duct. So obviously mass flow rate needs to be conserved. So m dot equals to C. So rho 1 A1 C1 must be equal to rho 2 A2 C2. This equation helps us in defining the mass flow rate in a one-dimensional duct, and also you can find the parameters like velocity at the outlet given the conditions at the inlet are known. So this is a first conservation equation which is applicable to all the fluid flows. Now we can go for the second conservation equation. So once you are able to understand the velocity of the fluid flow, then we can look at the second parameter, which is going to be the pressure with which the fluid is flowing across a body. So let me take a small two-dimensional, maybe a model. This two-dimensional model represents the fluid particle, which is moving in a duct. So there are three kinds of forces that will act on this fluid particle. The first kind of force is the gravitational force that will act vertically downwards. So this is going to be G, and there will be the pressure force that will be acting on the surface of the body. So we will have the pressure forces acting on both the sides, and obviously the differential pressure will be in such a way that the fluid particle will move in the direction as shown in the figure, maybe something like this, given the condition P1 is greater than P2. So there is going to be the pressure force that will be acting on the body, And the third kind of force is the viscous force, which is the amount of fluid friction that is exhibited between the layers of the fluid itself. So we are going to have a resistance force, that is going to be our friction force. So according to Newton's second law, we have summation of forces that are acting on this particular fluid particle equals to mass times acceleration, the net acceleration produced by this fluid particle. So you know what are the different kinds of forces acting on the fluid particle. The first force is the pressure force. I can write it as P1 minus P2 multiplied by A. The second force that is acting vertically downwards is the gravity force. So I can write mass times gravity. See, we understand that the gravity is acting vertically downwards, but the pressure term is taken as a I vector component. So this is the component of force that I have taken into consideration. So what I will do, I will just write this in terms of x. For example, if the fluid is going to rotate about its position, then obviously the acceleration component will also have a change of its direction. So I will just consider the x component of the force and I will write the equation. And the third component is the frictional force. I will write it as Ff. If you want to know what the frictional force means, you have to use the equation tau is equal to mu times dou u by dou y, which is the Newtonian law of viscosity. From this point, we can have F divided by A equals to mu multiplied by dou u by dou y. And the frictional force can be derived as Ff is equal to mu times A multiplied by dou u by dou y. So obviously you will be able to understand that there are three components of force which are contributing to the motion of the fluid particle, and if the particle is going to accelerate with an acceleration a vector along the direction of x, then that can be written as a combination of the pressure force, the body force and the frictional force experienced by that fluid particle. So by using this equation, you will be able to understand the behavior of the pressure inside the fluid particle or the fluid path zone at any particular moment. That can be calculated using the momentum conservation equation. And now we will go to the final conservation equation, which is the energy conservation equation. The final equation that we are going to see is energy conservation, which is quite important equation when you are speaking about the temperature changes that happens in a fluid. For example, I am going to have a duct and the fluid is going to pass through this duct. Then the term of energy that we can use in order to study this is the term called enthalpy. So maybe let's say H1 is the initial enthalpy and H2 is the final enthalpy. Now supposing that the duct is completely isolated or adiabatic, then the energy equation becomes H1 is equal to H2, supposing that it is only the enthalpy that is taken into consideration. But we know that whenever there is a fluid that is flowing with an initial velocity u1 and maybe at the exit there will be a change in velocity that will change to u2. So definitely the components of velocity will come into picture. So we will have u1 squared divided by 2 plus h1 equals to h2 plus u2. So it is basically a governing equation which is constructed upon the fact that energy is always conserved in case of any kind of system, whether it is maybe a solid system or a fluid system or a gaseous system. So finally, in order to conclude this, I will just write the basic equations of conservation. The idea behind writing these conservation equations is that if you are going to solve any particular fluid problem with the help of a computer, then you need to feed these equations to the computer, and the computer will be able to understand your physical case and then solve the problem, give the parameters for you. So the final conclusions from this particular session is that mass is getting conserved, force or the momentum, maybe I can write it as m dot v, that is getting conserved, and energy, maybe you can say it as energy flow rate or energy, they are getting conserved. So but we cannot very generalized, we cannot say it in a very generalized way. We need to make use of the differential equations and the forms in order to apply it to the computer, in order to make sure that the computer is able to solve the problem. So with this I think we can conclude this lecture. Thank you.